We're going to start with a simple animation. Imagine you're standing at the edge of a cliff and you're going to drop a heavy object and watch it fall. If something like air resistance is small enough, this is a good example of constant acceleration. And by that I mean the downward velocity is changing by the same amount each second. A situation like this is referred to as free fall. Free fall is defined as any situation when gravity is the only force on an object. Let's look at that fall in more detail. Many people have done experiments like this and they've all had similar results. What we're going to do is as it falls, we're going to track the speed each second. The instant we let go, we'll call that time 0. The object at that moment will be at rest just for a moment, so we'll call that a speed of 0. 1 second later, the object's going to have a speed of about 10 meters per second. 2 seconds later, its speed has doubled to 20 meters per second. 3 seconds later, it's now 30 meters per second. There's clearly a pattern here. Each second was a change in 10 seconds. Let's use what we learned about constant acceleration in our previous video to determine the acceleration between any of these 2 points. Let's just pick point 2 seconds and the point at 3 seconds. Remember that for a constant acceleration, you just find the change in velocity and divide it by the change in time, which produces a result of 10 meters per second, which fits the pattern that we saw. I need to remind you that in this situation, the assumption was that gravity is the only force. So things like air resistance are considered small enough that they are not significant. Because gravity was the only force, this 10 meters per second is referred to as the acceleration due to gravity. A more common way to see that is 10 meters per second squared. This number pops up so much in physics that it's been given its own special symbol and name, g. You've probably heard of g-forces before. That's in relation to this g. I do need to point out, however, that g does not mean gravity. I often hear people use it that way, but they're not the same thing. Gravity is a force. G is an acceleration. We call it the acceleration due to gravity. So force and acceleration are not the same quantities, so g is not gravity. It is, however, related to gravity, obviously. The questions are going to start now. So the first question I have for you, are all falling objects in free fall? It's a little counterintuitive, but the answer is no. No, they are not. Free fall, remember, required that gravity must be the only significant force. So what other force could be significant when an object is falling? The answer is, of course, air resistance. Air resistance is often referred to as drag. So to have a situation for free fall, we need to be able to ignore air resistance, or in other words, it needs to be small enough that it's just not significant. So when can air resistance be ignored? Well, the only true situation that you can ignore air resistance is in a vacuum. A true vacuum would be the absence of any air, so there's no air to cause any resistance. You're more than likely never going to find yourself in that situation, so we should consider other instances when air resistance is simply small enough to be ignored. So I'm going to change my question to when can air resistance be approximately ignored? There are actually a lot of situations where this is true. One of the big keys is objects need slow speed. Air resistance is significantly increased with speed, so if you're going slow enough, you can reduce that to a point where it's not having a large effect. Another issue is smaller objects will have less air resistance than bigger objects. You could also say that shape is important for air resistance. This is where the idea of aerodynamics comes in, but we're not going to get into quite that much level of detail. So here I'm going to perform an experiment. I have a golf ball and a ping pong ball, and I'm going to release them at the same time, and we're going to watch them fall. I measured them and found that the golf ball is about 17 times heavier than the ping pong ball. With that in mind, I want you to try and answer, if I release them at the same time, which ball will hit the table first? Well, let's check it out. That happened really fast. It did look like they hit at the same time, but it's so fast that it's hard to tell. So what I've done is we're going to watch in slow motion. To me, that's pretty cool. When I first let go, it seems they were pretty much even in the horizontal position. I do have to mention that's actually harder than it looks. You have to tell your brain to tell your hands to release at the same time. I'm really good at physics, so I was able to make it work. Just before they hit, it looks like they had pretty much the same position they started with. So to me, that's evidence that they hit at the same time. That brings up the question then, why didn't the much heavier ball hit first? Isn't that how things work, that the heavier objects fall faster? Turns out that the answer is no, not under certain situations. In this case, we can consider them to have been in free fall. That would mean that they had the same acceleration. Gravity was the only thing acting on them, so it was pulling them down with the same acceleration. If they had the same acceleration, they had the same change in velocity per time, which means they were traveling the same speed when they hit the table. Of course, these results would change if we use the larger height. You would expect the golf ball to pull ahead in that case. As they speed up, the air resistance would start to become noticeable. What's interesting about that, though, is it's not that the ping pong ball has more drag. They would actually have very similar amounts of drag for the same speeds. If the golf ball were to go faster, it would actually experience more drag than the ping pong ball. The reason why the ping pong ball would start to trail and the golf ball would start to lead, though, is because the heavier golf ball is simply less affected by the amount of drag that it experiences. Here's another question. Does an object have to be falling to be in free fall? Well, let's just consider that situation. Here I'm going to throw an object up into the air. I bet it's driving you crazy that that's not coming down. To answer the question, no, an object does not have to be falling to be in free fall. The condition was simply that gravity must be the only significant force. So if I can drop an object and have gravity be the only significant force, why would it be any different going up? So when we say free fall, you have to be a little bit careful with that. It's kind of an unfortunate word. It's a little counterintuitive. It doesn't actually mean falling. Let's go through this motion a little more in detail. And again, this is an experiment that's done many times, and people always get similar results, assuming that air resistance is small enough. This time we have to start with a non-zero upward velocity because we're of course throwing it up into the air. We're going to track each second what the velocity is. 1 second later it will have slowed to 20 meters per second. 2 seconds later slowed to 10 meters per second. And then at 3 seconds it will reach a speed of 0, which means it's at the peak of its throw. It's achieved its maximum height. At this point, notice that the object is temporarily at rest, and so essentially it turns into a fall problem like we started with. If you drop an object at rest and it falls down, that's what this problem is turned into. So let's consider that. If we assume air resistance is negligible, how long will it take for the box to return to its launch position, and what speed will it have? Just as a reminder, I'm throwing it upwards with the speed of 30 meters per second. We've already gone through the first part of this, and there's the second. What we want to find is the time it took, the total time, and the speed it had when I caught it. Okay, we've already gone through this, so I'll sneak through that part. Now, on the way down, the pattern should repeat itself. I mean, what reason would it not? We're assuming air resistance didn't have any influence on this, so there's no reason why it shouldn't be the exact same pattern. So 1 second after our 3 second peak was reached, it's increasing to 10, then 20, and then 30. So it's just double the time that it took to go up. Notice that the velocities are not the same. The speeds are the same, but the velocities are different. It started upward, and now at this point it was heading downward. So the answer to our original question was 6 seconds and 30 meters per second. A follow-up question I want to ask is, at what point is the acceleration the smallest? I'm going to give you a few seconds to think about that. A common answer I hear is it was the smallest at the top. In fact, a lot of people say that the acceleration was 0 at the top because it has a velocity of 0. But with an understanding of acceleration, that actually doesn't make any sense. A speed of 0 means it's stopped. An acceleration of 0 means it's not going to change that speed. So if it had a speed of 0 and an acceleration of 0 right there, it would be a box that's hovering in the air, and we just don't see that, unfortunately. Remember that gravity is the only force this whole time, and it's always applying that same acceleration. So to answer this question, at no point will it be the smallest. It's all the same. That's why this pattern is so symmetric, because the acceleration is constant. We're going to do a slightly different situation. This time I'm going to drop a heavy object, and it's actually going to hit the ground at the bottom of my cliff. As I dropped it, I was careful to note the time from when I let go to when it hit the ground, and found that it was 4 seconds. Can I use that information, 4 seconds, to determine the height of the cliff? There's a useful relationship between the height an object is dropped from and the time it's falling. This comes from the connection between position, velocity, and acceleration. If I were to show you the derivation of this, I would need calculus, so we're not going to go into that, but that doesn't stop us from using it. We know the time that it fell, so we can find the height of the cliff. Notice I'm using 10 meters per second squared as my value for g. My units of time will cancel out, and I'm left with 80 meters. That's a decent sized cliff. You certainly wouldn't want to jump off that. This relationship is useful, and it's one that you should probably remember. I found an interesting YouTube clip as a final demonstration of freefall. I mentioned earlier that the only place you'll truly find freefall is in a vacuum. And while we'll probably never find ourselves in one of those, there are some large vacuum chambers in the world. In this clip, this guy takes a bowling ball and a feather and drops it from a large height in a giant vacuum chamber. Here's a close-up of the feather and the bowling ball right before they're released.
Four. Counters on. 2, 1. Release.
Look at that. They came down exactly the same. Wow.
I really like this video. The music has a nice touch. The one thing I find funny about this video is at no point do they show a real-time view of the drop, just the slow-mo. But I still think it's pretty cool. I'm going to stop there. I hope you enjoyed my brief explanation of freefall. Remember, freefall is not necessarily falling. The only requirement is that gravity is the only significant force on an object.